I'm Dr. Muhammad Shoaib, and today we are going to study Jablonski diagram. In other words, it can also be said as fate of excited molecules. First of all, this diagram was drawn by a Polish physicist Alexander Jablonski, who is called as father of fluorescence spectroscopy. Nowadays, it is more correctly called as Perrin-Jablonski diagram because a French physicist, Jean-Baptiste Perrin, contributed a lot of points and modified it. It is a tool for the understanding of possible transition in an excited molecule. That's why we say that it shows the fate of excited molecules. These are the contents which we will study here. First of all, absorption of light and excitation to a higher energy level. When a molecule absorbs a photon of a particular energy level, it shows transition. This transition is shown by the straight arrows pointing upwards. An electron is excited from lower energy level to higher energy level. This bold line shows electronic energy level. It is the ground state electronic energy level. It is the first excited state electronic energy level. A electronic energy level further consists of various vibrational energy levels, which are shown by these green lines. A vibrational energy level further consists of different rotational energy levels. So here it is the ground state in electronic energy level. It has various vibrational energy level, and the vibration energy level has various rotational energy levels. There can be two types of transitions. As the name shows, transitions mean changes. These transitions can be radiative transitions, where the energy difference is emitted or absorbed by photons and are represented by straight arrows, upward arrows or downward arrows. The second one is non-radiative transitions. This is the transition without absorption or emission of photons and is represented by undulating arrows. What are singlet and triplet states? If the two electrons are paired, this state is called as singlet states. They can be at ground state singlet or they can be excited state singlet. But in both cases, their spin is paired. One is clockwise and other is anti-clockwise. And if the spin of two electrons is same, that is unpaired spin, that is called as triplet state. And that will only be an excited triplet state, because it is not possible for two electrons to have the same spin state in ground state. These are shown by S0, S1, S2 for ground singlet state, for first excited, for second excited singlet state. It does not have T naught. Singlet has paired spin but triplet has unpaired spin. Here is no net magnetic field because the magnetic field of each electron cancel out each other. And in a triplet state there is a net magnetic field. In singlet state there is no net angular momentum. Here there is a net angular momentum values. In singlet state the overall spin quantum number, the value of spin quantum number is 0, plus half and minus half. And in excited state triplet or triplet state, a spin quantum number has 1. More importantly, it shows one spectral line, that is why it is called as singlet. And it shows 3 spectral lines, that's why it is called as triplet. Most molecules have electrons in their singlet states. There are few exceptions to these most of the molecules, and oxygen molecule is one of that exception, and it has electron in its triplet state. What is vibrational relaxation? As the name shows, an excited electron can be relaxed, can come to lower in vibrational energy level. First way the energy is lost is through vibrational relaxation. It is a non-radiative transition from higher vibrational energy level to lower vibrational energy level within the same electronic state. It can be in S1 or S2 or S3. Excess vibrational energy is lost to the vibrational modes either intramolecular or intermolecular, and it keeps on losing its energy through vibrational relaxation until it gets to the lowest vibrational level of the electronic state. It is very rapid, and the time it takes to complete is 10 to the minus 12 to 10 to the minus 10 seconds. Second is internal conversion. It is the most common transition which we all know. In simple words, we can call it de-excitation. It is also a non-radiative transition between two electronic states of the same spin multiplicity. We can say a molecule from the higher electronic state is converted into the lower electronic state. The process is called as internal conversion from Sn to Sn minus 1. It is again followed by a vibrational relaxation so that the electrons or the molecule is in its lowest vibrational energy level, that is, it must be more stable. Next is inter-system crossing. It is weakly allowed. It is a non-radiative transition between two isoenergetic vibrational levels belonging to the electronic states of different spin multiplicity. Usually, this intersystem crossing is when an electron comes from the higher or excited singlet state to the triplet state. It is in competition with other internal conversion and fluorescence. It is too slow because it is weakly allowed, or we can say it is forbidden transition. So it is very slow, and its relevance for the majority of the organic molecule is 0. And again, after ISC, internal system crossing, molecule immediately releases its energy through vibrational relaxation and comes to the ground vibrational level of T1. Here, first of all, It is absorption and excitation, as shown here. Then from higher electronic energy level, an electron can come to the lower energy level. It is called as internal conversion. From higher states to the lower state of same spin multiplicity, it is called as internal conversion. What is vibrational relaxation? Within same electronic energy level, when an electron loses energy from the higher vibrational energy levels to the lower vibrational energy level, it is called as vibrational relaxation. Third one is intersystem crossing. When when an electron comes or shows transition from one spin state to another spin state of the same energy, it is called as intersystem crossing. And then there is the phosphorescence. It is also a type of intersystem crossing, but when the electrons from T1 comes to the ground state, this intersystem crossing is called as phosphorescence. And phosphorescence is a radiative transition between two electronic states of different spin multiplicity. The emission of photon from T1 to S0 transition is known as phosphorescence. It is similar to intersystem crossing and it is weakly allowed. As it is weakly allowed, so its rate constant is very slow and occurs on a much longer time scale than fluorescence, which will we see in the next slide. Fluorescence. It is a radiative transition between same spin state S1 to S0 and its time scale is 10 raised to minus 10 to 10 raised to minus 7 seconds. Its time scale is very low, that's why it is very rapid. Again, as a consequence of the vibrational relaxation and internal conversion, fluorescence occurs. And it occurs from the lowest vibrational energy level of the first electronic excited singlet state to the ground state singlet. And here is a famous Kasha rule, which states that the fluorescence or phosphorescence only occurs with appreciable yields when the lowest excited state of a given multiplicity. Jablonski diagram represents energy level within a molecule. These energy levels are singlet state, triplet states, or vibrational states. Every column usually represents specific spin multiplicity. Within each electronic energy states are multiple vibrational energy states. As electronic energy state increases, the difference in energy becomes continuously less. As the electronic energy level gets closer, the overlap of vibronic energy level increases and they come closer to each other. Here is the main Jablonski diagram. This purple arrow shows the absorption from ground state electronic energy level to the excited state energy level. These are singlet. Then there are different possibilities. One possibility is internal conversion. If it shows that the excitation from higher excited state to the lower state, it is called as internal conversion. And when this internal conversion comes from S1 to the lowest or ground state, that is called as fluorescence. These are similar, but when there is a ground state, it is called as fluorescence. Next is vibrational relaxation. Within same energy level, when the relaxation occurs from higher vibrational energy levels to the lower energy level, it is called as vibrational energy level. In S1, the vibrational relaxation is shown here, and in T1, vibrational relaxation is shown here. Here we can see that it is the V0, V1, V2, V3. Here are different vibration energy level a, within T1. Next is intersystem crossing. Intersystem crossing is when the transition is in between the different spin states. When the transition is in between the different spin multiplicity. From S1 to T1, it is intersystem crossing. And when this transition is between T1 to S0, as it is a ground state, so this intersystem crossing is called as phosphorescence. And that's all about Jablonski diagram. I hope that you got my points. Thank you.